Okay, and we're good. All right, before we begin, any questions before we begin? How things are going to work, or anything we talked about last time? I guess not. So the first few topics. The first few topics that we're going to do, they are sort of a review. So you're kind of expected to know them, with probably the exception of 1.6, although I'm pretty sure you would have done that in precalc, talk about block functions. But definitely everything else you should sort of be familiar with already. So it should be nothing new. So I'll kind of go through those relatively quickly because I don't expect anything to come as a surprise to anyone. But we'll see as we go on. Before we begin, though, I just want to talk about calculus. Last time I did a little story on calculus. So, does anyone know what calculus is about? Like, what is calculus?
The measurement of change.
Measurement of change. That's half the answer. Not specific, you know. Derivatives is a big part of it. So that is half of it. It's actually a little less than half. Integrals is really a really big topic. Right, so calculus is really the study, if you want to be really like minimalist about it, it's the study of limits, which we'll talk about in chapter 2, what a limit is. The two main styles of calculus is the two main tools that we use. They're called the derivative and the integral, and they're both actually limits of functions that we will talk about later on. Right? So the derivative is the tool that we use for half of calculus. It's not quite half, but it's called differential calculus. Right? This is the part of calculus that deals with rates, how fast something is changing, the rate of change. Right? So you know, in life, everything changes. There's a law of entropy. Things break down and decay over time. Things are always moving, things are always changing. Calculus, part of it is the study of change, right? How fast are things changing? What's going on over time? That's a big part of calculus. That's the point of, half the point of this class, to figure out how fast something is moving, and on top of that, to be able to predict movement, right? To know that, okay, based on what's going on and what has been going on, we kind of think this will go on in the future. And that helps us to plan for things ahead of time. That's called differential calculus, where it talks about dealing with the rate problem, right? The rate of change, how fast something's moving, right? And this could apply to a lot of things, right? You could analyze the weather based on the rate of change, right? You can analyze stock market prices, right? You can analyze how certain medications diffuse in a patient's blood system, right? Or how fast is a cancer growing? So how long you should tell that patient how long he has to live, right? All these things, they're always changing. Calculus helps with that. It's called differential calculus. And in calculus 1, most of what we'll be doing is differential calculus. So it will seem very disproportionate, but actually the second part of calculus is pretty big as well, probably a little bigger. That's called integral calculus. Now what that half of calculus deals with is the area problem, talking about how much space something takes up, or to measure a certain amount of space. And of course that in itself is important. There is something called the fundamental theorem of calculus, which Newton and Leibniz figured out. And it's kind of why when people talk about calculus, they sort of think Newton and Leibniz invented it, you know, independently. They didn't really invent it. Calculus has been studied in these two different areas for centuries, right? Archimedes knew how to do calculus, right? But Newton and Leibniz are the guys who are responsible for really realizing that these two different fields of study, figuring out how fast something moves and how much space it takes up, they're actually connected, right? They're actually kind of the reverse of each other. And that is called the fundamental theorem of calculus, which we are also going to talk about in this class. And so Newton and Leibniz were one of the first groups to realize how these guys are connected, and they intimately define the relationship in which they're connected, and that's why they're kind of considered the fathers of modern calculus. But there are really two different problems that we will be trying to attack here. How fast something is moving, and what predictions we can make based on figuring out how fast it's moving, and how much space something takes up, and applications of those two. And the fundamental theorem of calculus that connects these gives us even more applications that we can apply to. There are going to be lots of things that we're going to be doing with calculus in this class that you probably never thought we could use calculus to do. And so that's kind of where we're going. I know that's very vague and that's very general. That's sort of what it's about. Calculus is about figuring out how fast something is moving and how much space it takes up, and the applications of these two. Right? Also, before we jump into things, as I said, we're pretty much going to be doing a review so far, but I thought I would talk about skills. You need for this class. And pretty much if you're not a math major, these are the skills you need for any math class you'll ever take. So, as I was saying last time, there's a lot of misinformation of what it takes to be good at a math class, right? What are the actual skills you need, and how do you actually achieve these? And I told you, I spoke about the advice that you might get. Oh, just do a bunch of homework problems and you'll be fine, and do this and that. Right, these are not comprehensive. So I'm sort of going to tell you what skills you really want to acquire while you're studying, so you know if you're doing it correctly or not. There are two main things that you need to be good at for this math class and pretty much any math class. And for a lot of classes, these are literally the only two skills you need to know. One is form recognition. Two, algorithm example. That's it. You want to be an A math student? Master those two skills. That is it, right? There's really nothing else. Of course, there are a lot of skills that support these, but those kind of aren't really things I can talk about in general. They depend on the person, and I'll talk more about how they would depend on the individual student. But once you can do these two things, you're golden, right? Form recognition is basically being able to recognize a certain form when it shows up. Algorithmic execution is knowing how to deal with that form to accomplish a certain purpose. Right, so that's pretty good news. You only need two things to be good at math, right? And so that smart kid in class that you think, oh, he was born knowing math ever since he came out of his mother's womb, he's not better at math than you because his IQ is higher, or his brain is bigger, or he's just smart. He's better at math than you because he has these two skills, and he can apply them in a math class better than you can, right? So that's the good news. You only need two things to be good at math. Here's more good news. Everyone in here already has these two skills. Yes, everyone, even you. You already have these, and I will prove it to you right now. What is this? Chair. It's a chair. Very smart. This is brilliant. Okay. And what is this? It's another chair, right? Just keep things simple, right? Don't make it complicated. We're already in math class, right? How do you know that this was a chair? It looks completely different from this. It's a completely different color, made out of different material. How do you know it's a chair?
It has a seat, but its purpose is
it's the same.
The purpose is the same. It has a certain form. It has a certain thing, a quality of being a chair that you can recognize. There's a flat part for you to sit down on, and there's a backrest, right? And you can have these things looking very different, but you can really see they're kind of the same thing, right? That's form recognition. If you can recognize the difference between these two and still know that they're chairs, you're good enough to take care of one, right? The difference is knowing how to do it in a different context, the context of a math class. Now, what's a part of form recognition that's important is not only being able to recognize what something is, but being able to recognize what something isn't, right? So what is this? It's a table or a desk, right? In particular, it is not a chair. Everyone follow me so far? Okay, all right. Now, it turns out with a desk, this is a peculiar kind of furniture. I can kind of use it as a chair, even though technically it's not a chair. I could sit on it, right? So even though technically it's not a chair, I can sort of manipulate it or take advantage of the situation and use it as a chair if it's convenient for me, right? But at the end of the day, it's not a chair, and I need to recognize that, right? but sometimes I can use it as a chair, right? So being able to recognize what something is, knowing when something is a chair or a desk or a blackboard or a piece of chalk, and knowing that it doesn't matter the color, how it looks, what it's made out of, if you recognize the basic form and function of the thing, you know what it is, right? Being able to just recognize that is enough. And as you guys demonstrated, you guys have that ability. The difference is you want to bring this ability to your math class. So, for example, so let's deal with one form. So let's do some examples. What is this? It's called a quadratic equation, right? We know it's a quadratic equation because it has a certain form. There are coefficients in front. The x is what I'm going to consider as being my variable, right? So notice that here I have x to the second power, and it's followed by a term that doesn't have an x in it. There's an x to the first power. In front of it is a term that doesn't have an x in it. Here, technically there's an x to the 0 power, but you won't see it. But you can kind of think of it as one term has x to the second power, one term has x to the first power, one term doesn't have an x in it. This we call a quadratic equation. Okay. I'm going to try to trick you guys, right? So pay attention right now. Wait for it. What's that? It's a quadratic equation, but it looks totally different from this one.
The numbers, the terms, the different, the coefficients.
Yeah, but you can still recognize this as a quadratic equation, right? It has the form. What about if I did this? Now I just renamed my variable to y. It's still a quadratic equation, right? Or if I did this? What's that? Still a quadratic equation. What's that? Still a quadratic equation. Because we know the rules of math says we can add anything in any order, right? So the fact that I can rewrite it to look like in this order, basically I just know a form, right? I know that anything that has this form is a quadratic equation. It does not matter what the A, B, or the C looks like. It doesn't matter how scary it looks. It doesn't matter what letters it has, as long as the letters aren't the X. It is a quadratic equation, right? So this gives you a form that you should be able to recognize in various different contexts. Just as you can recognize the difference between these two chairs and know that they're both chairs, you should be able to recognize that these are all quadratic equations, even though they might look very different. They might look really scary. The thing about calculus is there are going to be a lot of things that look really scary, but they're not scary once you know the basic form that you're looking at. Right? You just need to be able to identify that. What about that? It's a cubic. In particular, it's not a quadratic equation, right? So now, when we have quadratic equations, what are some things we can do? If I want to solve that quadratic equation, what can I do to solve that quadratic equation? I can try to factor, right? That brings us to two algorithms. Now, I assume you all dressed yourselves today. Is there anyone who didn't dress themselves today? Okay, if you can get dressed, you can follow an algorithm, right? An algorithm is just a sequence of steps to accomplish some goal, right? So you know how to get dressed. You know that you have to put on your socks before you put on your shoes, right? If you know how to make dinner, if you know how to get to school, you know to get on the bus, follow a set of instructions to go from point A to point B, you can follow an algorithm. Everyone here has the skills. So now, for example, if you see something like this on a test, the first thing you need to know is recognize what is it. it's a quadratic equation. Once you recognize it's a quadratic equation, you automatically know a bunch of algorithms that you can apply to that quadratic equation if you want to solve it, right? So one thing would be you could factor. And apply the zero factor system. Right, so you factor it, you set each factor equal to 0, you solve for x. What's another option? You could use a quadratic formula. Right? Quadratic formula. Any other option? You could complete the square, which is kind of reinventing the wheel for the quadratic formula. This formula is actually derived using completing the square. But you could complete the square. Right? So you see this thing on a test, it doesn't matter how ugly it looks, you need to first recognize, hey, it's a quadratic. Once you recognize it's a quadratic, hey, these are my options, right? Now, in particular, if you're looking at the polynomial equations, which we'll talk about what polynomials are later on, one would apply to a polynomial equation. Two, however, is very specific to quadratics. I could not apply this guy to this function. It would not work, right? So if I recognize, hey, that's not a quadratic, it would never occur to me to try option 2 on a math test, right? I just know whatever I'm going to do, it's not going to be that. It has to be something else. I'd probably try this. Complete the square also won't work on that one either, right? These two are very specific to quadratic equations, right? So I see a form, hey, it's a quadratic equation, I automatically know what algorithm to go with it, right? Now, for forms, what helps you with that is, one, you need to know, actually, I'll talk about that a little bit. Here's something else I want to, another important skill, which is, now you're going to see the point why I asked you about the table. What is this? It's what's called a Quadratic Equation, right? So fourth power. It's not a quadratic. However, if you want to attack something like this, how would you do it? We could think of it as a quadratic, right? I could look at x squared as the variable instead of x and realize that this is what I have. Right? So I have a variable squared, a variable to the first power, and a term that doesn't have the variable in it, right? So technically it's not a quadratic, but I can sort of think of it as a quadratic. In the same way that this table is not a chair, but sometimes I can kind of use it as a chair, if it's convenient enough, right? Once I realize that the highest power is double the next power, and the next term doesn't have any variable, I can think of that thing as a quadratic, right? The same thing I could do with, if this was a 6, that was a 3. Technically, it's not a quadratic, but I can think of it as a quadratic. And in that case, these algorithms will apply to the variable that's here, right? I just think of x to the 6 as x cubed squared, right? Now, we can get to what we need for the form, what I'm going to get to. You need, of course, algebra, right? This is why algebra is so important to calculus and everything else, right? To be able to do this manipulation, it actually takes some algebraic knowledge to do that. You need to be aware of the rules governing exponents, right? So you're going to need algebra. Algebra is going to help you recognize a form because quadratic equations, you deal with that in algebra all the time, you deal with that in precalc all the time. That's why you guys even knew what it was when I asked you about it, right? So you're going to need your algebra. What else are you going to need? You're going to need to know definitions. In some sense, concepts, which will kind of help you with word problems, right? So these are some supporting skills that you need to know. So for example, If you've never seen a quadratic equation before, but I gave you a formula and I said, this is a formula that defines a quadratic equation, you should be able to recognize, oh, these are all quadratic equations, right? So you need to know your algebra because sometimes you have to manipulate things to look like a form that's familiar to you. And you need to be able to recognize that form in the first place. It's a form that you would have learned from algebra class. You also need to know your definitions. So when I'm telling you definitions in class, it's important that you actually learn the definitions and you learn them exactly, right? Just as in the case of a quadratic equation, options 2 and 3 apply only to quadratic equation. If something was off by just a little bit, right? If this 3 was instead of 2, that's a difference that you need to recognize, and you need to recognize that that makes it untenable to deal with as a quadratic, right? You need to really recognize the form, know what it really means to be a quadratic in its essence, right? That's form recognition, right? And these are the skills, these are the supporting concepts that you need to know. And of course, you need to be able to memorize these, which, again, is another skill that everyone here has. What about again, here you need algebra. You need algebra to work for it. You just need algebra for this class. Algebra is the guide where you learn all the rules. You learn the rules of arithmetic. You learn the distributive law. You learn how to factor. You learn how to divide. You learn how to multiply. You learn how to add and subtract various kinds of functions. Right? And so, yeah, you need to be able to recognize a form, and you need to be able to apply a certain algorithm that applies to that form specifically. Right? Now, as we go on, after we get through the review, and even while we're doing the algebra review, not a comprehensive review, but just a few things that you need to know. You are going to be given rules later on, where I'm going to tell you, okay, when we're doing derivatives, here's a rule that applies to polynomials, right? It does not apply to any other function. It applies to polynomials. So you have to be able to recognize when you're looking at a polynomial, and then you have to know how to apply that particular rule to a polynomial. If what you're looking at is not a polynomial, the rule does not apply, right? And these are things you're going to have to be very specific with. So for example, the rule will be very different for x squared as opposed to 2ax, right? So if you see this, you're going to apply the rule in a certain way, right? Because that's a polynomial. If you see this, you're not going to apply that rule. You're going to apply a different rule because it's not a polynomial. This is an exponential function, right? So if I give you a function and I say differentiate, you need to first recognize what is the form of that function. Is it a polynomial? Is it an exponential? Is it a log? Is it a rational? You need to recognize that form. Once you recognize the form, you're going to go through with an algorithm. The algorithm is going to be given by, it's going to either be a formula or a sequence of steps, right? A lot of times in calculus, in the case of calculus, the first step, just one step is going to be the calculus. The rest of it is going to be algebra, right? So the calculus, we're going to pretty much boil it down into just formulas. You know, if you have this kind of function, this is the formula that you use to get this result. Right? But you have to recognize that. And you have to understand that things might look scary. I might have a 2/3 here, or you know, a radical 2 here, and the rule would still apply. You need to not be afraid of the particulars, how it looks. You need to look at the general form. Just as how you could figure out these are chairs, even though they look very different. This one, you're not scared by, oh my God, my brain shut down, I'm so afraid, I blanked out, I've been studying all night, I just can't recognize what this is. No, you understand what the form of a chair is. You understand its function, so you'll be able to recognize it even when it looks different, right? So once you have those two skills, that's what you're going to need. These are the things that you're going to need for this class and any other math class you're doing. So now going back to the general advice that you might hear. When someone tells you, oh, to be good at math, you need to practice a lot. You do all your homework problems. It's not just blindly doing homework problems. There is always a goal. There's always going to be a goal for anything you're doing. When you're practicing problems, you are going to practice them until you master these two skills for the particular topic that you're working on. If you can't recognize a form and an algorithm to go with all those things, you haven't studied enough, right? If you do one problem and you can recognize these, you've studied it, right? There's no magic number of problems that you have to do. Sometimes you might have to do all the homework I give you and more. Sometimes you don't have to do all the homework, right? You do it all just for the grade, because, it will be incomplete. But you don't have to do it, right? The point of doing a lot of problems is for you to just recognize the different contexts in which a form can happen, right? Eventually, you doing a lot of problems will make you recognize a quadratic equation, even if I reshuffle the terms. Because after doing 50 problems, you just realize, oh wow, that's what a quadratic equation is, right? And you're going to keep practicing until you can see that, until you can know what a quadratic equation is, no matter how ugly I make it look. That's what you have to strive for. You're not studying in a vacuum. You're not just watching YouTube while doing your homework just to get through it, just to get the credit, right? Because that's not going to help you on a test. You are practicing with two goals in mind at any given time. You need to recognize a form, you need to know what algorithm to go with that form, and you need to be able to execute it, which is going to take algebra skills. Okay? So at any given time when you're studying something in this class, these are the two skills that you should be aiming to master. Form recognition, algorithm execution. And of course in your next class, in your next math class, you're going to need that as well. So I just wanted to throw that out there, because I realize that that's a stumbling block for a lot of people. A lot of people, again, the advice goes back to, believe in yourself and be positive and all that. You need to recognize certain forms. And so, for example, if I give you something like this, and knowing formulas and forms is going to be very important for when things get a little bit hairy. For example, it's not a terrible looking thing, but just to illustrate the point, right? If I ask you to expand that, right? A lot of people might forget, God, it's a cube root of 2, and there's an x cubed under a radical. It does not matter, right? What do you see when you look at that? A minus b squared. And do you know what that is? What's the algorithm that goes with that form? Right? It does not matter what the A looks like. In this case, that's your A. It does not matter what this B looks like. In this case, that's your B. If you see something here, minus something there, and there's a square, you're going to take this guy, put it here, take this guy, put it here, take this guy, put it here, take this guy, put it here. Right? Don't freak out, oh my God, Professor, we never looked at that kind of function in class. It does not matter. It has a form that goes with it. Right? So once you really understand form and algorithm, it doesn't matter what I throw at you, you're going to be able to figure it out, right? And I know a lot of people Professor, when you teach us something in class on the test, you need to put the question in exactly the same. You know what? Life doesn't work that way. Your problems in life that you're going to encounter don't come pre-packaged in a way for you to recognize. You're going to have to figure things out at some point, right? But you need to know what things are. Did someone raise their hand? I thought I saw something. So, again, you're not studying in a vacuum. This is the point. You need to get these two things when you're studying. And of course, you need to understand the purpose of why I would tell you certain things, like why I would tell you a definition or why I would expand on a concept, is because I think it will help you to accomplish these two things. So that's just some things to keep in mind. Things are going to look a lot scarier than they actually are. But that should not stop you, right? Once you recognize those two things, and again, that's where the individual would come into play, right? So you know that the two skills that you need to be good at this class, but the thing is, not everyone would acquire those skills in exactly the same way, right? You need to understand yourself, how you learn, Do you need flashcards to remember a form? Can you just hear audibly, right? Can you just watch a YouTube video? Do you need to read it, actually physically write it down in notes and read it? right? You need to know what it is that gets you to achieve those two skills, right? So that's where the difference will be. And some people, it might take longer, it might take shorter, but you can do it, right? It's up to you to just know what the goal is and do whatever you have to do to get there, right? So in that sense, I can't really give any general information because it really depends on the individual. But everyone needs to get to those 2 points, right? The difference between someone who is good at math and someone who's bad at math is those 2 things, right? So a lot of people might freak out how something looks, but to me or anyone who's an A math student, they'll just, oh, it's just an A minus B all squared, right? I know how to do with A minus B all squared, right? So I know how to deal with that, right? A lot of things in math, it's just about pattern recognitions and forms and twisting things. Once you know how to deal with a simpler case, you automatically know how to deal with all the complicated cases that have the same form. Okay? So that was just a little, didn't even start the material yet. I'll probably jump into it right now. Okay. So again, that's another thing. Nothing is random. At any given time, you need to know how to use the information I give you to accomplish those 2 things. Right? That's what you're always aiming for. Those 2 skills are what you're going to need. And so right now, we're going to start with our first topic. We're going to review functions, because functions is what we're going to be playing with a lot of time. And again, it shouldn't be anything new to you at this point. It's just a lot of definitions to regurgitate. So one thing that's at another level, it's kind of the same thing, but word problems, right? Dreaded word problems. Right? When you're attacking word problems, you're still looking for the same 2 skills. The only thing is, there's something that comes before that. You need to translate, right? So word problems has this additional translating supporting skill, right? You need to understand what certain words mean in math, right? Because certain words might have certain meanings, you know, like a product means multiply and things like that. Once you know how to read English and translate it to math, then you get to this point, right? So when I give you definitions and concepts, that's also what I'm trying to help you with. I'm trying to explain something in English to you so that when you read it in a word problem, you'll be able to kind of translate it to a form. Once you get a certain form, you know what algorithm goes with that form, and you'll be good. So we're going to start with section 1.1. It's functions and their representation. Do you remember what a function is? Can you give me a definition? Function is a rule, right? That assigns to each element in the set. This set is called a domain. A set is just a group of objects, right? Exactly one element in another set, and that set is called the codomain. So I'm defining like 3 or 4 things in this one definition. I'm telling you what a function is, and I'm telling you what a domain and codomain are. The particular elements in the codomain that are assigned is said to be in a set called, what's this set called? Range. that's what a function is. Right? So there are a bunch of ways that we can represent these. Do I need to talk about all of these? Let's get that first one. Functions arise. Why do we care about what functions are? This is a very general and esoteric definition, but there's a point to it. Functions, functions arise when we try to model. Right? This basically means going from a word problem to a mathematical formula that we can apply an algorithm to. Model the relationship between objects. Calc 1 and 2 deal with what we call single variable functions. This is, as opposed to multivariable function, which is calculus 3, which if you're here, you probably don't need to do that class. So a single variable function which are functions in which one variable depends on one other variable. So if you're reading a word problem and you realize, hey, these two things are connected by some relationship that I can write down as a rule, it means you should be able to form a function that describes that relationship. And you should be able to get to a formula, means you know what algorithms to apply to. I haven't said anything strange so far, right? Like everyone knows what a variable is and don't need to be. So, illustration here. Here's a set, which is a group of things, which I can call a domain of a function. And here's a set, another group of things, which I can call the codomain of a function. So there are a bunch of guys in here, where to each individual here, I'm going to assign it to someone else over there. And there might be guys over here that didn't get assigned. Right? They're just hanging out. These guys that did get assigned, I think of them as being in another group that I call range. That's sort of pictorial representation. Functions are often given names like F, G, usually lowercase letters. Also, generic elements from the domain and range are also given names. At At this point, it's worth mentioning that the form of a function is what matters, right? The actual letters that I use to describe any of these things don't matter. Just like something doesn't have to be a certain color to be a chair, right? So these names are, you can rename a function anything you want. You can name a variable anything you want. Typically, not always, right? Don't get confused if it's not true. X is, represents a domain element. It's called the independent variable. So you'll hear me mentioning that all the time, independent variable versus dependent variable, right? So a guy here, I could call him X, right? And there's a guy over here, I can say is a corresponding element, I can call it Y, or f of x. So x is often used, but it doesn't have to be used with x, especially if something like time is what you want your independent variable to be. It could be t, or it could be anything else. Y represents a order element, or let's be more specific, range element. And this is called the dependent variable. Recognizing who's the independent versus the dependent variable is going to be very, very important later on, especially when we're doing something called implicit differentiation. We're going to need to be able to recognize who's the dependent versus the independent variable, and it's actually going to change how you view things. Something you'd want to know. Another name for this guy, you might call this the input, right? The guy that you're plugging into something, and you might call this guy the, although we often omit the word corresponding. Call this guy an output. So pretty much the word domain, how you want to think of it, is the set of possible inputs. And this would vary with the kind of function that we're looking at. Range is the set of corresponding is to our and one is. Yeah, I'm a math teacher, I don't really know it's outputs. Yes, this is taking a while, but this is language I'm going to be using throughout the class, so I really want to have it in writing what it is. First, other things I might say. Notation. We may write something like y equals f of x. So let's drag it over here. To refer to a function whose name is f. X is the independent variable. And y is the dependent variable. So basically the guy that goes here, that's your input. The guy that comes here, that's your output. And this here is the name of the function. This notation, don't let it confuse you whenever it shows up in a certain context. Sometimes brackets beside something means multiply. This does not mean multiply. You want to kind of think of this as plugging into the rule that this is. So this represents the rule that we have, which has a certain name. This represents the guy that we're plugging into the rule. This represents the output that you get as a consequence of following the rule. What else do I need to explain about? Is called a mapping diagram. Functions are sometimes called mappings, but I won't call it that in this case. Now it turns out for functions, they have certain kinds of mapping diagrams. So there's something that is a function versus something that is not a function. So things that are functions are things like one-to-one mapping diagrams. So one guy connected to one guy connected to one guy connected to one guy. That's called a one-to-one function. That's going to be important in some context. You can also have a many-to-one function. So you can have two guys in your function going to the same output, and that's fine. So this is called many-to-one. Things that are not a function is something like a one-to-many. So if you have one input going to two different outputs, it's not a function, right? So you can't model it as a function. Or something that does not use up all its domain elements. So if there's a guy in the domain that doesn't get assigned to anything, it's not a function either. So that's the sort of concept that can tell you about is there something? So that's a concept that can help you to identify a word problem, for example. Depending on the relationship of something, you can know whether something's a function or not. And once you know it's a function, you can write a formula for it, and once you have a formula, you can get an algorithm to go with it, and all that stuff. So that's one representation of a function. It's a mapping diagram. So if you're given something like that in your homework, you should be able to recognize that it's a function and deal with it in that sense. And you can have other representations of functions. So a function can be presented to you in several contexts. You need to recognize when one is being presented to you. Other representations. The first one I'm going to skip. It's kind of silly to keep repeating that at this point. We're in calculus. One set of points, or what we call coordinates. Right? So for example, I can tell you, here's a function f, and I can define it as something like 1.2, 2.3, 3.4. I can just give you a list of points, and that would define a function. That would define a function, for example, that has the domain, in its domain has 1, 2, 3. 1 is mapped to 2, 2 is mapped to 3, 3 is mapped to 4. So that's what it means. Here, the first coordinate is the input. That's how you want to think of it, the second coordinate is the output. So that's one, yes?
What does it mean for something to be
Onto means everyone in the codomain is also in the range. Right? It means there's no guy over here that gets left out. We're not going to talk too much about onto functions in this class. We might mention onto one. But onto means that everyone over here gets assigned to someone over there. Let's. Or you can also say something like F is. I can write a formula here. X for X. Such that X is in the domain. You might have it written as shorthand or given some function. What else? Another way to represent a function. Algebraic. Now when we say algebraically, we mean using a formula. For the function 1, and give me a formula to describe that function. F of x equals, for that guy over here. F of x equals what? X plus 1. Right? So, if someone gave you a state, hey, here's a function, you might need to transform it to a formula to be able to do something with it, right? For this function, that would be your formula. And you say that this is an algebraic representation of the function. It's basically a formula, right? That tells you a rule. It says whatever your input is, you're going to take that guy, you're going to add 1 to it, right? So if you started with a 1, you're going to add 1 to get a 2. If you start with a 2, you're going to add 1 to get a 3. If you start with a 3, you're going to add 1 to get a 4, right? So this formula actually describes to you the rule that you're trying to apply to this function. So that formula is telling you something to do to the input, and it will give you a particular output, right? So that's called an algebraic representation. 4, 3. Because I skipped the first one because it was silly. I do know how to count. There's a numerical representation. Basically, when you have this, you have a table. A table with a list of values. So, an example here, again, going back to this function. Table where you can say, okay, in this column I'm going to put the x's, and here I'm going to put the y's. 1, 2, 3. Over here I have 2, 3, 4. Right? Listed as a table, right? We call that a numerical representation. There's another representation. And at any given time, you should be able to switch between any of these representations from one form to another form. There is the graphical representation. It's just a visual representation. So again, for this function, f of x equals x plus 1, what would be the picture for that? What would it look like? It goes like this. Straight line going up here. It's going to pass through the number 1 here. What's this horizontal line here? called the x-axis, right? That represents where your input function comes from. So for example, if I plugged in a 1, the output would be 2. Plug in a 2, the output would be a 3. Plug in a 3, the output would be a 4, so on. And this vertical is called what? The vertical axis? That's called the y-axis. That's where you list all your outputs, right? So at any given time, if you're given a numerical set of data, you can plot points. These coordinates will tell you what points this picture will pass through, right? And sometimes you might look at a random list of numbers and it's just a list of numbers. It doesn't mean anything to you. But then you draw a picture of it and you can recognize some sort of pattern. For example, this is called a linear function. Linear functions behave in a certain way, right? And just knowing that this is a linear function, if you give me a huge table of lots of numbers, I don't know what they're doing, but then I draw a picture of it and I realize, oh, they're all on a straight line. I automatically know everything about that function, right? I know the slope, I know the y-intercept, and I can predict any value that's along that curve, even if it wasn't given to me. Another representation. Here's the verbal representation. Right? Basically, what we find in word problems. So, you might say something like, let F represent the temperature at time t. So you might see a phrase like that or something similar in a problem. And basically what that means is you're looking at a function called f of t, right? Which means you can put t's over here in the table, you can put x over there, you can plot these numbers, you can draw them in a graph, and if the numbers are nice enough, you can figure out a formula for f of t. You might be able to say f of t equals some formula, right? But sometimes they might say it in a phrase, oh, this is that, right? And here you can see that there's actually a relationship. There's a relationship between f and t, right? At a certain time, there will be a certain temperature that you can measure with a thermometer. Right? So there's a relationship between these two. There's only one guy here and one guy there. This you can think of as the input, that you can think of as the output, right? Because the time is the independent guy. That's not the one you have control over, right? You'd have to look at the time to see what the temperature is, right? And so if I'm given a sentence like this in a word problem, I would think of this as a function, and I know that on my vertical axis, I would put temperature. On my horizontal axis, I would put time. Once I get to a picture, there are a bunch of things I can do. There are a bunch of things I know about pictures that I can apply algorithms to. There are certain forms. Yes?
You said time would be on the y-axis?
I would put time on the horizontal.
Oh, okay.
So remember, horizontal is the x-axis. X represents the input. Input we think of as the independent variable. It's usually the guy that you don't have control over. It's independent of anything, right? And then this y is what depends on this value. Right? So very usually, in pretty much all cases, time is an independent variable. It's not something we control. It just keeps going. And other things would depend on what time it is. In math, graphs and formulas, those are typically the most useful forms, not always, but very usually. So the idea is, given any random problem in this class at least, if I describe anything to you, you're going to either want to represent it as a graph or as an algebraic form, right? Because these are forms that you know how to deal with. You know algorithms that go with these things. So I could give you a huge table of a list of numbers, but if me telling you that, hey, this actually represents y equals x squared, you automatically know a bunch of things that go along with that. You know what the picture looks like, you know how to solve for x, you know how to do everything. So these are the two the forms that you're going to need to translate things to. Right? Those are the ones that are going to be most useful to you. And of course, you should be able to translate from a verbal description to one of those two descriptions. And let's actually practice some of that. So enough definitions, enough talk. Let's put some of this into practice. So here I just described a situation to you, and I described it in words. This is a scenario. A suppose H represents the number of hot dogs sold at price P. Right, so here I'm defining variables for you. I'm defining who's my interpret B. We'll talk about that a little bit later. Pretend I don't want to sell anything for anything other than $2 or $3, right? I'm either going to charge $2 or I'm going to charge $3. What are the domain and range of this function? Probably write this down because I'm going to have to erase it to actually start doing the problem. Let's see. Assume on the price and H and P have a linear relationship. What is the best price? So this is a word problem, as you can see. That's kind of the way in how life would present the problem to you. I can come to you and say, man, I got this side hustle on the weekends, I sell hot dog, I've been tracking how many I sell, and I realize, that when I charge $3, I can sell like 50 in a day. And if I charge $2, I can sell 80, right? And so I can give you this information. Now, one thing you will recognize from the scenario is that there is a relationship, right? There is a relationship between the price I'm charging and the amount I'm selling, right? Notice that if I vary the price, the amount I sell will also change. So there are two objects here being related. One is the price, one is the number of hot dogs sold, right? I have one thing depending on one other thing. It means I can represent it as a function, right? So me just reading this is telling me there's a function that can describe the situation, right? Whereas, okay, so now we realize that there is a function that can represent this situation. I'm giving a name to this, h and p. Now, what do you think are these variables? H represents the number of hot dogs sold at price p. Interpret h of 3. So A, what would h of 3 be? A. So if I ask you about what is h of 3, interpret that value. What would it be? In English.
The number of hot dogs sold at $3.
Huh? Number of hot dogs you would sell at $3. Right? That's how you're going to think of it. H is your output, right? H represents the number of hot dogs. Notice that in this is just like your f of x. I'm telling you, this 3 is the input, that's the output. The H, I know is my output, that represents the number of hot dogs, which means the guy in here is really a p-value that I put in here. So this is going to give me, the answer is going to be the number of hot dogs I sell when my price is 3, right? And in fact, I actually know what that answer is. This is actually 50, right? But more important than knowing what that number is, you need to know what that number represents based on how the problem is being set up, right? So there are a lot of times where I give you this scenario, but you're the one who's going to set up your variables. You're going to say, okay, I'm going to call this the output, I'm going to call that the input, and you have to interpret, give meaning to these numbers somehow, right? So that's what h of 3 would represent in this case, right? So this is saying the number of hot dogs you sell when the input is $3, right? Okay, B. Let's talk about the domain and range of this function. What is the domain of the function h? What is the range of the function h? Right, domain is 2 and 3. They're the only two prices I'm going to sell. Those are the only two inputs for my function. Right? And what would be the range? Right, 50 and 80. It's a set. I don't have to put them in a particular order. So yeah, the domain is just these two numbers. These are the possible inputs. These are the possible things I can put in that bracket. Right? That will make sense in this one. Yeah.
Shouldn't the range be P? Yes.
Yes. No, this is fine. This means the domain of the function h. This means the range of the function h. It's a notation thing. Yes, the actual list in here, these are p values, whereas these are h values. Right, but this is a notation. This is called the domain of h. You always call it by the name of the function.
So the top part will be H of P, not the 3.
H of p is the whole thing. It's always h of p, no matter where I am. Because once I define h to be this and p to be that, and I write it as h on the outside and something else in brackets on the inside, I'm already saying this is my output, that's my input.
So it's the H is the output of the price P.
Yes. So this is saying when p is 3, my h is 50, right? When my input price is 3, my output number of hot dogs is 50. So that would define the domain and range. The domain is the possible inputs, the possible things I can plug into this function, possible things I can put here. The range is the set of corresponding outputs. If I put in a 3, the output is 50. If I put in a 2, the output is 80. Now let's attack the last problem, which is really what Jhevon would be interested in. What's the best price? How would you go about figuring that out?
Based on the output,
What information do we know?
we know that $2, the output is 50, and at $3 the output is no.
Yeah, at $3 the output is 50, at $2 the output is 80. What else do we know? Are we going to help Jhevon make the most money on these things? Huh? What else do we know? It's a linear relationship. What does that tell us? What does it mean to have a linear relationship? Okay. Tell me about what its formula might look like. What would its picture look like? Yes? It means it's a straight line, right? So how would we go about doing that? How would you set this up? Let's draw a picture here to represent this so you can see what's going on. Okay. What's actually on this axis here? The horizontal.
On the outside, in the part.
Price. The p-values are going to be here. Those are the guys that go inside here. That's the notation. H would go on this side, right? Okay, so let's put in our 2 points. We have a 2 and we have a 3. 2 gives me what? 2 gives me 80. Right, so that'll be 1 point here. 3 gives me 50. Right? So that's information I know just by me telling you that information. Now, other things we can extrapolate by me telling you what kind of relationship it is. When I say it's linear, it means what? These 2 points are connected by a straight line. That should be a straight line. Right? So that would kind of tell me, I can assume if I sell for like $2.50, I can kind of figure out approximately how many I expect to sell, right? I can predict how many hot dogs I would sell for a given price by knowing this relationship. Yes?
I know the relationship.
I told you in the problem. Oh, well, you need a lot more data points, right? A lot of times math is useful in approximation. If you took hundreds of samples and you realize they all kind of fall on a line by just plotting it, you realize, oh, we can just approximate by linear and we can use it. Right? In this case, I told you. In practice in real life, you'll just take a bunch of measurements. That's where statistics and probability comes in. You take a bunch of measurements and you can guess what the relationship is. And you'll do that in your science classes, especially like chemistry, things like that. Where you're trying to guess a relationship. In this case, I told you, in real life, you'll just take many more measurements to come to that conclusion. But okay, so far I know that. So how is that going to help me? Does that picture help me say what price I should sell? No. So what price should I charge for the hot dogs?
But you could tell that the higher the price, the less hot dogs you make, because it's decreasing.
Okay.
But you can't.
I can.
Yeah, because it's price of the house.
You gotta find how much you make.
The higher the price, yeah.
Right. The best price would be the one that makes me the most money. How would I figure out how much money I actually make by selling a certain amount of hot dogs? Multiply what?
80
times 3.
That's only 2 points, but what if those aren't the only thing? I'm willing to vary the price. I want. Huh?
You can test out the
Would it be like a read?
Well, how would I know what point? So let's say, oh, I'm willing to sell at $2.50. How would I know what the output is? Should I figure it out? How would I figure it out? Find a formula for the line. I need to go to the algebraic representation, right? That's the guy that tells me how to find things pretty easily. So how would I find the formula for a line? I know it looks like y equals mx plus b. I know that's the formula, right? That's the form. Once I know something is linear, I know that's its form. In this case, it's really going to be h equals np plus b, but whatever, right? Doesn't matter how the thing looks if it's a different name. That's the form I'm going after. Now I need to know what is the n in this form. This is the slope. Do I know a formula for the slope? Right, y2 minus y1 over x2 minus x1, or in this case, h2 minus h1 over p2 minus p1, right? B is going to be the y-intercept, which I can find after I find this. So let's start there. What is my slope here? h2, which is what? It's going to be 50 minus h. Let's call this p1, this is p2. The corresponding, so this is h1, this is h2. Okay, so this is going to be 50 minus 80 divided by 3 minus 2, right? So that's going to be what? Minus 30. Now how do I find the equation? I could use like a point slope form, right? I know that h minus h1 equals n p minus p1, right? Y minus y1 equals n x minus x1, right? Where h1, p1 is a certain coordinate, n is the slope. So now I can plug these in. Take any point, let's say I take h1, that's 80. The slope is minus 30. P minus p1, the corresponding value for 80 is 2. So then I know my h is equal to minus 30 times p minus 2 plus 80. What is that? That's minus 30 p. What would that be? Plus 140. Right? Distributive law, minus 30 times minus 2 gives me positive 60 plus 80 gives me positive 140. So h is equal to this. I have found a formula that would describe how many hot dogs I would sell at a given price. Okay, now I have that formula. How do I figure out what price is best? How much money would I make? I'm just going to randomly plug stuff in. You wouldn't need math if you're going to randomly plug things in, and you'd also spend your entire life trying to figure out basic things. No? What? Well, a table would involve you plugging in random things. How do I know what I'm aiming for?
You could set h equal to the amount of money you'd ideally like to make.
$1 million.
Well, realistically.
No, there's a better way.
When you take one of the values, T2 and 3, because that's all the values you
No, what if selling more than 3 would be worth? Or selling less than 2? We don't know. How do I figure it out? How do I know how much money I make? What's the technical term for how much money you make at something? Profit, yeah. Directly the amount of money I make before cost. It's called revenue. All right. See, I'm selling these hot dogs. I'm not paying taxes or anything. Right? The most money I make is the revenue. This is how much I make just by selling my things. How would I figure out the revenue? It's a different function, right? Let's name that function R. How would I find R, the revenue? How much money would I make in general? Yeah.
H minus 140 over negative 30. No, actually.
No, that would give me price.
Yeah.
How much money do I make? H times P, right? Figure out how many hot dogs I sell times what price I'm selling them at, right? That would actually give me a function. Do I know what H is? Sure do. Just figured it out over here. What do I know about quadratic equations? That's a form I know right now. What I know about that particular kind of quadratic equation, what would it look like? What would that look like? So now let's say I'm doing the revenue function, so that's my price. What would it look like? The graph of quadratic is a parabola. How would it look?
It's like that. It's gotta be upside
It'll be
down.
It's upside down because this is negative. Algebra people, you need to look up your algebra. Right? It's going to pass through 0. Right? How do I know that it will pass through 0? Well, I can factor, right? I can factor out e, I can minus 30e plus 140. Okay? And then I can set that equal to 0 to figure out where the points are. This would give me p equals 0, or I can set this equal to 0, so p would be 140 over 30. Right? Which is 14 over 3. Right? So this would be over here, 14 over $3. Now, looking at that picture, do you kind of see where I want to be? To the very top. I want to make the most money. I want to find that point. How do I find that point? Yes, for a quadratic, it is the midpoint. More specifically, how do we get to the midpoint? What's that point called on a particular quadratic? Let's say it didn't even intersect the horizontal. How would I know that point? The maximum. Do we know a point for the maximum of a quadratic? Formula or anything? That's called the vertex. We want this. Right? That's the most amount of money I would make. I want to pick that price. That's going to make me that money. Right? How do you find the vertex? There's a formula. Right? So if you have ax squared plus bx plus c is y, then for the vertex, what do we know? X is equal to minus b over 2a. So in this case, the vertex occurs when p is equal to minus 140 over 2 times negative 30, which is minus 60. So that's 14 over 6, which is going to be what? 7 over 3, which is going to be what? Roughly? 2.33. If I want to make the most amount of money, I need to sell my hot dogs for $2.33. Right? And I didn't guess that, right? Imagine how many guesses you try before you figure that out, right? I don't have to guess it. I translated it to a picture, translated that to a formula, and the formula told me exactly what I needed to do, right? That's the power of math. That's why we need it, right? It's not just to torture you. Math people invented it just to torture us. No. It gives us useful information about the world. And remember, this all started with a word problem. I had a problem. I sell hot dogs on the weekend. I want to figure out how do I make the most amount of money. The trick is realize what depends on each other, setting up a function, going from a picture to a formula. Using that formula gets me the best price. Right? Did someone? Yes.
How did you get X intercept?
The X intercept?
There, 14 over 3. How did you get that?
Oh, I factored.
I'm sorry?
I factored. Right? Remember, these intercepts happen when the function is 0. So basically what happens is I set r equals 0. And I'd have a quadratic equation, something equals 0, and I solve that. In this case, I had two terms with a common term p. I factored it. So I said each factor equals 0. P equals 0, or this thing equals 0. If this thing equals 0, this thing equals 14. So I know it's going to. I know that I should be selling at some price between 0. I'm not going to give the hot dogs away, certainly. and 14 over $3. The best price, $2.33. That's going to make me the most revenue. So we kind of see the idea here. Now, at this point, yes.
You know, it was kind of confusing because I assumed based on the question that you were asking what was the best price between $2 and $3.
No, the question started with, suppose Jhevon is willing to vary the price.
Oh.
Right? That tells you I'm willing to not sell it at $2 or $3. Right? Someone, I don't think he's here. Remember that there was a student over here in the first class who, he read the syllabus, he was trying to be facetious, like, does that mean you could drop the final? Right? It comes down to being very specific, right? Math talks about being very specific. You have to really read the problem and know what things are applying. So I told you that I could vary the price, right? In part C, I told you that, I'm only willing to sell for $2 or $3. But in part B, I said that. But in part C, I said, assume I will vary the price. What is the best price, right? So it means I can go other than 2 or 3, and I just want to find out what's the best price, right? So yeah, that's how we figure it out. I think we will stop there for now. But again, we kind of jumped into deep water here. Later on during the semester, we're going to learn how to set up certain kinds of functions to deal with word problems, and these are going to be the important things. So I will see you guys if there are any more questions.